Assalamu alaikum. In this lecture, we are going to cover a few topics of Module 1 of EEE 4505. I hope you remember in the introductory class we have discussed how we have arranged the contents of this course into few modules. Uh, so we will begin our studies from Module 1. If you look at the topics of Module 1, these are the topics that we are going to cover in Module 1, and let's see how far we can go in this particular lecture. Okay, let's begin with this topic. It says mathematical modeling and engineering problem solving. Okay, if we look deeper into this, it means that any problem that can be thrown at us can be eventually break down into a mathematical problem. In most of the cases, we are engineering students. The problems that will be thrown at us will be related to mostly engineering studies, and if we break it down into further lowest point, we will see that this is a mathematical problem. But now I will show you a hypothetical problem which can be modeled mathematically, and eventually the final answer lies into solving a mathematical problem. Okay, let's have a look at that problem. uh, this is the map of IoT, and in our day-to-day life in IoT, we encounter this problem. Let's say at some point in time we reach at this point A, and our destination is that point B. This is a very common problem that we face in our day-to-day life in IoT. And if you are at point A with a few of your friends, then you get two school of thoughts to reach this point B. Correct? The one school of thought says, let's move using this path and reach point B. Another school of thought says, no, we will go diagonally. We will start from this point and reach here diagonally. Okay. So both are correct approach. And how mathematics comes into here, let's look at it. Now, if I ask you which of these methods are most time efficient, or which of these methods uh, are actually efficient in terms of your now how now let's see how mathematics comes into this hypothetical problem that we face it in our day-to-day life. That if someone asks you, show me a time efficient method of going from point A to point B. Okay, so you have to prove that this diagonal distance is lower than covering. You have to show this diagonal distance is lower than these two sides. Okay, let's assume the length of this side is 1 kilometer, and let's assume the length of this side is 1 kilometer. So the problem that we are intending to solve turns into this. We have a right angle triangle here. We have to solve the value of the length of the side, this side. Okay, we have length of the side here at 1 kilometer, we have the length of the side here at 1 kilometer, and we are now here at the timeline of 2025. With all the technological advancement in our hand, we know, or with all the technological advancement in our hand, we can simply calculate the value of this length of this side applying Pythagoras theorem, and that will be root 2. And using our calculator, we can easily calculate the value of root 2 and say that this value is obviously lower than 1 plus 1, or this is obviously lower than 2. So that was one problem that we can, if we look deeper into the problem, that requires us to solve it mathematically. Now let us move back in time. Let's imagine the timeline is 2000 BC. We are living at the Babylonian civilization. Same problem has arisen here. During that civilization, people were very aware of the length of the sides of their piece of land. Let's say this is one piece of land owned by one of your friends, and you are here with your friend at point A, and you want to reach point B. Okay, your friend says, my friend, let's move in this direction, and then we will go in this direction. In this way we will reach point B. You argued with your friend that no, we will take this route and we will reach here in less time. Okay, the argument is valid, but remember the timeline is BC 2000. Okay, so how can you prove that you whatever you are telling is true? You will have to apply the same thing that you have applied a little while before. You have to show the length of this side is less than sum of the length of these two sides. Let's assume the length of these two sides are again 1 kilometer. This is a square land. So it all comes down to this point that you have to calculate the length of this side, and show that this is less than 2. Remember, this is BC 2000, and you have to calculate something that the people of that time haven't discovered yet. They know Pythagoras theorem. Remember what Pythagoras theorem says. If we have a right angle triangle here, and we know the length of this sides, let's say length of this side is A, length of this side is B, and length of this side is C, that C square will be equal to A square plus B square. And it has various proofs. But the problem we are looking to solve involves something else. It involves that we need to calculate the value of C here. We are assuming the length of the side is C. So how can we calculate C? Is root A square plus B square. Here the value of A is 1, value of B is 2. That means we have reached to a point that will require us to solve root 2, and we have to show that the value of root 2 is less than 2. How can we do that? Remember, I am again telling you the timeline is 2000 BC. And people back then didn't know how to calculate root of an integer. So here comes our numerical methods. Okay, so far what we have discussed, it was an attempt to show you that any problem that can be thrown at us, modeled mathematically, or if we dive deeper into the problem, we will see that that problem is basically a mathematical problem. And now we have reached to a point that we need to solve that problem. Okay, so now we will look at this topic, that basic concepts of error in numerical computation. Before we move into the basic concepts of error, let us look at the basic concepts of numerical computation. Where were we? We were at a point that required us to solve the value of root 2. And I am again telling you, we are at a timeline when people do not have any tool, any calculator, or any advanced algorithm to solve the root 2. Okay, so how can we solve this mathematical problem that is at our hand? So whatever we have discussed so far has come down to this point that we need to solve it, and using numerical methods. So people back then came up with an approach that they will initially approximate a solution. Okay, what was the problem? We need to calculate the length of this side C, and that in our hand was root 2. So we will have to approximate one solution and associate that approximation with an iterative formula That iterative formula will give us different solution at different stages, for example, and we have to check whether the solution of two consecutive stages are almost repetitive or not. If we reach at that point, that let's say at fifth iteration we have got some value 1.414, at sixth seventh iteration we have got one value 1.414, that means we have reached the end point. We can take that solution as our uh, solution of that particular problem, that we have reached to a point that gives us the value of roof. Okay. So that algorithm is called Heron's algorithm. If you look at internet searching for Heron's algorithm, you will find the concept. My handwriting isn't quite good here. I am using newer tools, so it will take some time for me to get adjusted with this setup. So bear with me. So the main thing here is that using Heron's algorithm, we will solve the problem that were at our hand. That problem said that we have to solve the length of the side C, and which is root 2. Let us first approximate a value. So our initial approximation will be Ci, or let's give it C1 in this way. No, let's give it C0. This is our first iteration. C0 is, let's approximate 0.5. So what will be the new value? How we will associate one formula with it? The formula will be average of two values. One is that old C0 plus 2 by the old value. In this way we will get another iteration, that is the new value of C. If we run it here, we have to replace C0 by 0.5 and also C0 here by 0.5. Let's see what we get. We have calculators at our hand. Okay, let's forget that for a moment. 0.5, and if we invert 0.5, that will give us 4. So we have to take the average of 4.5, that is 2.25. Okay, so now we have two values. That initial approximation C0 was 0.5, and after one iteration we have got a value 2.25. Remember this thing. In this way we have to run our iterations again. So for C2, what will be our calculation? We will have to take average of C1 and 2 by C1, which means we have to take 2.25 plus 2 by 2.25. So C2 is 1.44. Again, if you run another iteration, that C3 will be 1. C3 will be 1.4144. If we again run another iteration, that will give us 1.414213 in this way. So if we run again another iteration, we will get another value that will be closer to the actual value of root 2. If we run another iteration, we will get more closer to the value of root 2. So thankfully we are not in the Babylonian civilization. We have a calculator with us. We can have the exact value of root 2, that is 1.41421356, and let's say we were interested up to this significant digits. So if we run the iteration again and again, we will see that we can reach to the value closer to the actual value of root 2. So in this way, people back in the Babylonian civilization calculated root 2 and solved any problem that any engineering problem that eventually directed them towards this mathematical problem called solving root of a integer. Okay, there's an uh, there is a standardized version of this formula, that is this. Instead of, if you are asked to calculate the value of root 4, in that case you have to start with one approximation and then run the iteration, and here the value of n would be 4. Okay. Now we have learned a very basic concept of numerical methods, that in how we can approximate a solution and then plug it in with a formula and then run the iterations and see where we are standing and how close we can get to the exact solution. So our main idea, or our main objective was here to learn the basics of numerical competitions and also get familiarized with the concept of errors in numerical computation. Okay, so what is the error here? Look here, while solving the value of root 2, we started with a value, that is, we assume that the value of root 2 would be 0.5. Then we associated it with a formula that showed us the value of root 2 could be 2.25. And after that iteration, we reached to a point that gave us the value of root 2 as 1.44. So all these values are at some point in our computation gave us value of root 2, which means at each point, which means we obviously didn't reach to a point instantly where we could have the value exact value of root 2. That means at each stage there were some errors or some deviations with the exact value. That deviation is called an error, or we can say that, if we say it formally, this is the formal definition or the formal formula of an error, that at any point in our computation, the difference between the true value and the approximation gives us the error. And another way of calculating error is that fractional relative error. If we calculate the true error, this is the true error divided by the true value. That means the value that we are looking to find, that will give us the relative error, and this relative error can be represented in a percentage form. So that is percentage relative error. Okay. But there is an issue with this concept of relative error, because in most of the cases we might not know the true value that we are looking to get. And the problem we started with, or the discussion was there, we started our calculation looking for an answer of the root 2. We know the exact value, so in this way in each of the stages we can calculate the relative error as we know the true value, but it might not be the case for most of the numerical problems. In that case, what will be the relative error? In that case, the relative error is basically the difference between two consecutive approximation, current approximation, or the value that we have calculated most recently. That is the relative error divided by. There are two other errors that are associated with numerical methods. They will require a bit more in-depth discussion. So that will be discussed in the later part of the video. Thank you very much for your attention.